Well, welcome to the second lecture. Again, I just want to emphasize I'm happy to adopt, and if you want to ask questions, please feel free to do so. Today's main topic will be to discuss how we find binaries due to their electromagnetic emission. And yesterday we discussed mostly the orbital evolution of binary black holes coming from large scales to small scales, and I've been so far entirely discussing massive black holes. So just to wrap up the discussion from yesterday, and if you forgot since the last 12 hours, this was the highlight of, or the punchline is that there's a bottleneck in the pairing of black holes. They approach each other in a galaxy merger from large scales due to scattering stars. And then once they get close enough, they're driven by gravitation waves. In between is a bottleneck, and we hope that can be crossed by the gas which surrounds the black holes. And I pretty much ended with this plot, which comes from the two-dimensional hydrodynamic simulations and shows the torque maps. And these are time-averaged surface densities of binary black holes with two different disk temperatures. And this is the distribution of the torques, and I explained yesterday that this, for a very warm disk, where this aspect ratio is 10%, it leads to an out spiral. And then for cooler disks, which we think are more realistic, you actually get an in spiral. So there's a couple of things actually I want to say here, because some people came and asked me questions afterwards. And I think there's two things I want to explain. So one is why do I, well, first of all, let me just show this result that I just showed. You can do these simulations and measure the torques as a function of disk temperature, which is quoted here as a Mach number. So 1 over this number is so these three things are equivalent. The Mach number is the orbital speed of the gas divided by the temperature of the gas. And it's equivalent to the thickness, which is 1 over this Mach number, or the temperature of the gas. So this is an aspect ratio of 10%. This here is A dot over M dot measured in units of A over M. So this is a dimensional in spiral rate. It says for every gram of gas you accrete on the black holes, you change the semi-major axis, and as measured in units of, when the semi-major axis is measured in units of M. Does the plot make sense? So it's a dimensional orbital evolution rate. Over here it's positive. So these binaries are out spiraling in the warmer disk. These are in spiraling. And now you can ask, well, how fast does this actually take in real time? And that depends on entirely on this M dot. So how fast you're accreting, which depends entirely on how dense the disk you're assuming surrounds the binary in these simulations. So in these simulations, the surface density is essentially a scalable number, because as I explained, in this bottleneck regime, the gas doesn't self-gravitate. Its mass is much smaller than the black hole mass at any given time. And therefore, it's just simply, the gas in these simulations just reacts to the 2 point masses. And so you can scale its density, arbitrarily number you want. Of course, you can't make it arbitrarily large once its mass exceeds the black holes. You have to include in the simulation the gravity of the gas itself. But as I explained, that's only relevant on larger scales. Okay, so if you scale this disk density in a way that the accretion rate becomes roughly what we see in quasars, then this in spiral or out spiral rate corresponds to a few times 10 million years. So that's actually quite rapid. So these black holes, as you see, this dimensionless number is order unity. So these are out spiraling in tens of millions of years, or whatever difference from that number is M dot, and these are in spiraling. So the second thing I want to explain is some people asked, why do I talk only about torques? And so these are torque maps. And the way I think to think of this is actually, that's even clearer, is to simply say I have gas around the black holes. Each patch of gas exerts a force on each black hole, so you just have to sum up all the forces. And the gas is pulling the black holes in all directions, and the black holes are exerting force on the gas in the opposite direction. Now this force, if you think of the force on the gas orbiting in roughly circular motion, it has a tangential component from the black holes and has a radial component towards the center of mass. And people usually, traditionally, ignore the radial component. And the idea behind that is that this gas that's perturbed by the black hole, further out here, if you perturb it in the tangential direction, you change its angular momentum. If you pull a force on the gas in the radial direction, you cannot change the angular momentum. You can only change the energy. And the idea was that, so then the gas's new orbit, after this force has modified its orbit, in general can become bigger or smaller semi-major axis and can also become eccentric. Two numbers characterize a Newtonian orbit, energy and angular momentum. The idea was that if you change the energy, you don't have to worry about that, because the idea was that the gas must remain on circular orbits because it keeps colliding with adjacent gas. So you shouldn't be allowed to change the eccentricity. You should assume the gas is always on circular orbits. In that case, you only have to care about the tangential forces, which changes the angular momentum. If you assume that it's on circular orbits. And that's why people always talk about the torques. Now, but more generally, if you allow both the black holes and the gas to deviate from circular orbits, then now you should measure all the forces, and you should simply measure both A dot and E dot in these simulations. And so that's the last thing I want to explain here. You can repeat this kind of simulations, and the only difference in this suite of runs that I show here is that the binary that was inserted over here is not on circular orbits, it's on orbits of various eccentricities. So ideally, you want to take a black hole pair, put it on some orbit, and just in a live fashion, let it evolve self-consistently and modify the gas distribution and follow the binary as it evolves, changes its semi-major axis and eccentricity. But unfortunately, that's basically very hard because, as I explained, the orbital evolution takes hundreds of thousands or millions of orbits, and you cannot, that's too much CPU time. So what you can do instead is just have not a live simulation, but you insert a binary black hole in the gas disk with different eccentricities, and you just prescribe its orbit. And over 10,000 orbits, it won't change much, the orbit, but you can measure the forces and calculate both A dot and E dot. So, so this is the eccentricity of this binary black hole, and this is dE over d log m. So the change in eccentricity for each mass you accrete in log units, and this is the change in semi-major axis for each per accreted mass. So what you see here is something interesting. If you have a binary that starts with almost zero eccentricity, circular, then dE is basically maybe slightly negative, but it's zero. So these binaries here tend to reduce their eccentricities and go back to circular. These ones here, dE dm is positive, so they're actually trying to increase their eccentricity. If you start with a very eccentric binary, then again, the dE over dm is negative, so these tend to reduce their eccentricities. And this is the semi-major axis evolution. These are out spiraling, this is positive, and essentially all these binaries here are in spiraling. So now we have two conclusions from here. A, if the binaries are eccentric, so I described this panic that maybe gas actually prevents black hole mergers and we shouldn't build LISA, the detector, because there won't be mergers. So that's alleviated by lowering the disk temperature, and it's also alleviated if the gas, if the binary is eccentric, it tends to in-spiral. But furthermore, there's an interesting point that there's two stable values of eccentricity, circular, or this value of about 0.45, because higher and lower eccentricities tend to be driven to this value. So that means if you have a binary whose evolution is dominated by the gas, not by gravitational waves, then it will tend to become eccentric and quite significant, 0.45. And until the gas is dominant, it's going to shrink and at that eccentricity value, the orbit semi-major axis is shrinking. So the self-consistent solution here is that your binary is driven to this eccentricity and shrinking its orbit until gravitational waves take over, at which point gravitational waves, you probably heard this in the talks about gravitational waves, I hope, that gravitational waves circularize the orbit quite rapidly. Okay. So, any questions? Yeah.
But so you go to this kind of fixed point of 0.45,
yeah.
and then you shrink, keeping the eccentricity fixed?
Yeah. Yeah, because this doesn't depend on the actual value of the semi-major axis. So, I mean, if you only care about forming binaries and mergers, you can remember that binaries are generally in-spiraling as long as they have some eccentricity, but also they'll be arriving at the gravitational wave-driven regime with some high eccentricity. Okay, so to put all this together, I just want to transition to the lecture 2. So this plot shows a version which I showed yesterday from a 1980 paper, which showed that stellar scattering slows down and binaries stall. So these is a plot that's essentially conveying same information, but in more convenient units. So these are binary black holes of equal mass and different masses, 10 to the 3, 5, 7, 9. And this is how much time they spend in units of 10 to the 7 years at each binary separation, or correspondingly at each orbital period. Right? So once you specify the mass, then each separation corresponds to an orbital period or a frequency on this axis. So binaries come from the right. They shrink their orbit, increase their frequency, and shrink their orbital period. And this shows that the stellar scattering, which drives the binaries at large radius, they slow down. This is gravitational wave emission, and this rapidly accelerates the in-spiral. In between this bottleneck, and this here is the age of the universe. This here is 13 billion years. So these binaries would take more than age of the universe in this model to cross this bottleneck. And then the punchline from the gas, if you add in the effects of gas, scaling to accretion rates that we associate with quasars. If you're familiar with Eddington units, I think I'm not going to explain this, but most quasars with bright quasars are accreting somewhere at tens of percents of this fiducial maximum Eddington rate. So if you scale it to that rate, then this plot changes: stellar scattering, then gas-driven evolution, then gravitational waves, and you close this bottleneck. Now, if you want to find these binaries, just remember that we are looking for them with gravitational waves. So these here are the frequencies of millihertz regime. So LISA will see the binaries here. Pulsar timing arrays will find the more massive binaries over here at larger separations where they're in the nanohertz regime. And this band corresponds to orbital periods between 1 day and 10 years. So this is a band where you could hope to look for binary black holes on sort of human lifetimes. If the orbital period is much longer than a decade, it will take us a century to monitor objects and find their periods. If it's much shorter than 1 day, then it becomes harder to find the periods. But also, the second point on this plot is the lifetime. So this here is sometimes called the residence time. So how much you spend in each logarithmic bin of binary separation. And you can see in this unit it's 10 to the 7 years. This is 10 to the minus 3 to order unity. This 10 to the 7 years is an important number because this is roughly how long we think quasars generally last. This also corresponds to the mass doubling time of a black hole that's accreting at this fiducial maximum Eddington rate. So there's a simple way to read this diagram, which is if this number is, let's say, 10 minus 3 in units of 10 to the 7 years, which is the quasar lifetime, then this corresponds, then the number of these objects on the sky should be 10 minus 3 of the number of quasars. Okay, does that point make sense? Each quasar, if you associate, is lit up by a merger and lasts for a certain time, and this lasts for only 0.1% of that time. So this allows you immediately to say, well, these are maybe not super rare objects down to here. 0.1% of their number should be 0.1% of quasars, as long as quasars have to do with merging of galaxies. And here, at high mass n, the large fraction of quasars should be going through this phase. Okay, so questions about this? So now we should ask how we actually find these binaries. And I want to remind you of the motivation. So I won't go through this long list of motivations. I just want to emphasize there are two things, there's various things you can try to do. One is you can just try to find binary black holes in electromagnetic surveys, irrespective of gravitation waves. Or you can also try to identify a given gravitation wave source on the sky and find the corresponding host galaxy or source. So a one-to-one detection of the same source in gravitation waves and the electromagnetic observations. And I just highlighted here the examples. Some of the things that I said here actually requires or is much better to find the same exact source in gravitation waves and photons. The rest you could do perhaps by just finding the population of binary black holes in electromagnetic surveys and then separately in gravitation waves. So I won't go through this, but I think I want to just mention the most common example where you want to do the cosmology and you want to identify objects in gravitation waves and then measure the distance and their redshift. So actually, again, was this discussed last week, the standard sirens and the fact that you can measure distance to gravitation wave sources? Okay, so I think it's useful to show how simple the argument is. This comes from this paper in 1986 from Bernard Schutz, and it just points out that a gravitation wave source, or without anything else, tells you how far it is. And that sounds very counterintuitive, because usually in astronomy, you see a thing on the sky, and you know its redshift, because if you measure the spectrum, you can find the Doppler shift, but you generally don't know the distance, because it could either be a very bright source nearby, a bright source far away, or it could be a dimmer source closer to us. And therefore, we generally have the problem of not knowing the distance, but you know the redshift. So for example, the supernova people who won the Nobel Prize 20 years ago for discovering the acceleration of the universe, they basically did that, got the Nobel Prize because they figured out a way to measure the distance. Here, for this exercise, we have the opposite issue. We have the distance from the gravitation waves, but we don't know the redshift. So this is just two equations. This is the gravitational wave amplitude or shear or strain. And this goes with a bunch of constants times the chirp mass to the 5/3 divided by the distance, and then the frequency to the 2/3. This is the chirp mass. And then the chirp itself, which is the f dot, the change in the frequency, goes again like a bunch of constants times the chirp mass to the 5/3 times frequency to the 11/3. If you take these two equations and divide them by each other, then f dot over h is a constant times the distance times the frequency cubed. So the distance is simply a constant consisting of c and g and pi, and then times f dot f and h. So if you measure the frequency of the gravitational wave, the frequency evolution, and the strain, you get the distance. And intuitively, that's because unlike in electromagnetic observations, you cannot pretend that you're a brighter source farther away and get the same thing, because if you're a brighter source, meaning more massive, you chirp faster. So the chirp speed eliminates the degeneracy. So this is very good. If you find the gravitational wave source, you know the distance, but you don't know the redshift, unless you find the corresponding object or host galaxy and take a spectrum. That's why you require the multi-messenger astrophysics to do this cosmology with standard sirens. I just want to show you this plot also. I'm pretty sure you must have seen this. This is particular to LISA. This is the gravitational wave sensitivity of the LISA instrument, assuming 5 years of operation. This is frequency. This is the strain to which you get a signal to noise of 1. And these are evolutionary tracks of black hole binaries with 1 to 10 mass ratios at different redshifts, 1, 3, and 5. And these dots show 1 day, 1 week, 1 month, and I think this is the break here is at 5 years. So the gravitational wave sources enter the LISA band. They last potentially for months or years, and then they chirp through here in a year, or the heaviest ones in just weeks, and then they merge at the end of these lines. And so the idea is to catch them here, and then you want to find the electromagnetic counterpart. Okay. So now let's move to how what emission you expect from binary black holes and how you distinguish them on the sky from single black holes. Oops, this thing is very unstable. So just some more cartoons of what we hope to maybe expect, and then I go through some details. First of all, this is the cartoon picture of the binary and this gas, circumbinary gas disk with the morphology that's deduced from the kind of simulations I showed. So there will be presumably this disk, there are the streams fueling the individual black holes. There may be some gas in between. And these streams, which I'll highlight some more today, in the simulations, they're periodic. Plus, this black hole pair is orbiting. So you might hope to see periodic variability. And in fact, that's going to be the main thing that I will discuss. That we can try to find periodic variations. These numbers here are for a fiducial million solar mass typical LISA source. This phase might last 100,000 years in the LISA band. And then this is minus 10 years. So 10 years before a merger, gravitational waves become very strong and take over the evolution of the binary from the gas. And they cause eventually a merger. I will show you that 1 day before merger, you actually lose some emission because the binary outruns the gas and runs away. And that will be a peculiar feature, a disappearing black hole in the sky. Now there's a very interesting issue that in the last day or few hours, the gravitational wave emission is extremely strong. Maybe this was also discussed in some depth, but the characteristic luminosity in gravitational waves, which is basically the rest mass released on the orbital time at the Schwarzschild radius, is a dimensionless number involving only G and C. And that luminosity doesn't depend on the mass, and it's extremely large. And even if you take 10 to the minus 6 of the gravitation wave luminosity and somehow manage to convert it into photons, you should see a bright source on the sky, coincidence with the merger. I actually won't discuss this much because I am not aware of a physical mechanism that has been that somebody came up with to actually couple the gravitation waves to the surrounding gas. There have been some proposals, but I just want to highlight that there's a way potentially to create a bright source at the merger. Then there's very interesting possibilities right after the merger. Sorry, I keep asking this, but did you discuss recoil and mass loss? Okay, so this I will then just go through at the end of this lecture. But so here the merger happened, and the two black holes became one. They coalesced into a single remnant. But two things happen. The gravitation waves carry off energy, and the last burst of gravitation waves just takes again the inverse of that characteristic frequency. So for a million solar mass black hole, it's just a minute or so. And then in that minute, you radiate in gravitation waves a lot of energy, which must come at the expense of the mass of the remnant black hole. So usually the remnant black hole M is not M1 plus M2. It's M1 plus M2 minus of order typically 1%. And so you suddenly lose 1% of the mass at the center of mass of this thing. And that causes the gas to respond and try to expand. And I will show you that that causes shocks, which might create an afterglow. And not only do you lose mass, the gravitation waves, if you've seen mental pictures of it, it's not a concentric, axisymmetric set of circles that comes out of the merger. It's actually a spiral close to the black holes. The gravitation wave emission has a specific direction. And not only does it carry energy, it also carries momentum in that particular direction. So momentum has to be conserved. So the remnant black hole, to conserve momentum, recoils. And this recoil speed is also independent of the mass of the black holes, and is also some fraction of c, which depends on how asymmetric was this merger. This is a very interesting thing. Actually, was proposed a long time ago, 80s, 90s, that this recoil should happen. But you had to actually calculate, solve Einstein's equations numerically. And this was only confirmed, I think, 2005 or 6, when the first numerical simulations in general relativity could calculate the actual solution of Einstein's equation and how much momentum was carried off by the waves. And so this is typically hundreds or thousands of kilometers per second. And so that's actually quite relevant astrophysically. It's not a small velocity. And that also causes shocks in the disk. And then finally, on the time scale, which is longer, which is the viscous time in the disk, now you have a single black hole. So you shut off this propeller, the binary, which was creating this cavity. You've shut this off because now you have only one black hole. And so on a time scale, which can be of order years or a decade for a 10 to the 6 solar mass black hole, the viscous time here is this time scale. Like this cavity will presumably fill in. There's nothing more to keep out the gas. And then you return to the state of a normal single black hole quasar. So these are post-merger afterglows that you can try to look for, particularly if you have an actual gravitation wave merger, but even in perhaps without a gravitation wave trigger, in some electromagnetic survey, try to find these signatures. So let me discuss these signatures in some more detail, starting with periodic variability, which I think is the most robust thing we can say. So I showed you these three movies yesterday, how the gas actually accretes in ways that depends on the mass ratio. And it's qualitatively quite different. So these are very unequal mass binaries. These are equal mass binaries. And this is in between. The accretion here, if the mass ratio is below this value of 1 to 25 or so, you can see here this almost looks like a picture, not a movie, because accretion is very steady. If you move over here above this magic number of 0.04, you can see that the system became unstable and the accretion is modulated on the orbital timescale of this binary. And again, that has to do with the fact that there's no stable orbits around these Lagrange points, so there's no way for the gas to do what it does here, which is it slowly accretes through this gap and goes from the outer disk to the inner disk. This gas here cannot do that. It keeps being thrown around when it tries to go near these Lagrange points and flies back. And so the accretion is become very strongly modulated on the orbital period. This Q equals 1 regime is actually also very different. It remains periodic, but this cavity becomes very lopsided, and the accretion as a function of time has a different periodicity, which I will show in the next picture. So, maybe I'll show you this result. So these are accretion rate as a function of time in this intermediate regime, and then roughly the equal mass regime. This is m dot there are two black holes. So the green and the blue show m dot on the smaller black hole, the green, and the bigger the primary black hole in blue. These are normalized in m dot 0, so that's the accretion rate you would have if you only had one black hole whose mass was m1 plus m2. This is the same plot for a more equal mass binary. So there's actually very obvious features on this m dot plot. First of all, you should see the units on this axis. If this is order unity, that means this binary, when you replace one black hole by two black holes, visually it's very striking. It looks like the binary is trying to expel the gas and prevent accretion, but in fact the total m dot here is actually, if anything, even higher than m dot 0. So in fact this binary is extremely efficient in creating this cavity, but it's totally not preventing any accretion on the black holes. It's very inefficient in doing that. These are, by the way, orbits. So this is some random subset from 400 to 425. So this is over 25 orbits. You can also see that the accretion is modulated very clearly on the orbital period, and also that the green, which is the secondary black hole, is actually accreting a lot more than the primary, and the primary is quite steady. So that's kind of interesting, maybe counterintuitive, but basically one way to say what happened here in this so I'm not in this intermediate regime. This black hole is actually capturing most of the gas that's coming from the outside, and this one is capturing only a small fraction, and this is quite steady. This is fluctuating on the orbital period. I'm not showing this case because the accretion rate is very boring. It's basically steady. This is the periodogram, basically the Fourier transform of accretion rate as a function of time. And you can see very clearly orbital period and half the orbital period or twice the orbital frequency. When you move over to this one, which might be the most common case of a binary whose mass ratio is between 0.3 and 1, the accretion rate as a function of time becomes a little more jaggedy, but there are still clear periods. But now, visually, well, they're first of all, the sum of the two m dots again add up to about 1. So again, there's no reason to think overall that a binary black hole would be dimmer than a single black hole with the same mass. Here their accretion rates are comparable because their masses are comparable. But what your eye picks out is actually a period that's longer than the orbital period. And when you do a periodogram, you still see the orbital period and the half orbital period. Twice the orbital period. Sorry, twice the orbital frequency, half the orbital period. But the largest modulation occurs at some frequency, which is maybe 5-6 times the orbital period. And that's because, well, let's just go back to the movie I already showed. Yeah. I can just show this one, it's the same. What you see when the mass ratio is larger than about 0.3, some other physics happens which changes the evolution qualitatively, which is that the streams that are feeding the black hole, you can see that some of the stream actually doesn't get captured by the black hole, it's flung back out and hits the wall of this cavity. So some gas is captured by black hole, but some large fraction of the gas which is trying to go near the black holes suffers like a slingshot and is flung back out and hits the wall of the cavity. And that distorts the shape of this cavity. And you can show that there's actually a runaway feedback here, which is you push one side of the cavity away from the binary because of this stream impact, which makes, whenever you try to pull off the next stream from that side of the cavity, which is farther, that stream is weaker. The other side of the cavity is stronger. And so this kind of runs away. You keep hitting the cavity wall and distorting its shape by these outgoing streams, which then makes one of the outgoing streams weaker, one stronger, because it's not equal in all directions. And this kind of runs away. And this creates, which is better seen in the next movie. It's actually a little better seen in this movie, that the shape of this cavity, this is in the frame which is co-rotating with the binary. But you can see that the lump forms and is rotating around the binary, and it modulates the accretion, because if you're pulling streams from the dense part, it gives you higher accretion momentarily. And so this modulation is at the orbital period of the gas at the cavity wall, and it's the strongest feature in this periodogram. Okay. So the bottom line is that you can, in principle, look for quasars on the sky and look for periodicities and try to convince yourself that you're seeing binary black holes and infer their orbital periods from these kind of periodograms. I think I should just maybe point out that the actual shape, this is a much cleaner, more sinusoidal looking variability with a very clear almost delta function in the Fourier transform, whereas this one has like a lower frequency modulation which is more like a sawtooth shape, like burst, superimposed on a more noisy, more sinusoid-like modulation on the orbital period. So let's see. So I wanted to, before presenting these various results, I just want to make sure people know how we think single black holes operate as quasars. I think it's useful to show one slide, because we're going to replace one black hole by two black holes, and the idea is, can you tell the difference in observations? So just very quickly, has this been discussed by someone in the school? So I think this one slide is enough, but what I'm saying so far is here, in the middle of a galaxy, there's a supermassive black hole surrounded by an accretion disk. I kept emphasizing that we're interested in the relatively small compact disk, which is not self-gravitating, fueling the black hole. Further out, there's gas that's supplying matter to this disk, and this gas is absorbing the radiation from the black hole and is being ionized, and the recombination of the ionized gas gives you recombination lines. And close to the black hole, the gas motions are very rapid, so the lines are reflecting these large Doppler broadenings, so you get broad lines, broad emission lines. Further out, the gas is moving more slowly. It's still reverberating the ionizing radiation from the quasar, and the recombination lines from here will be narrower. The whole thing is enveloped in an obscuring torus, presumably gas, and as I emphasized earlier, here stars are forming because the gas that would try to become a disk and fuel the black hole further out is self-gravitating, has a lot of mass, becomes unstable, and then somewhere form stars. Stars explode as supernovae, form dust. And so this region is more complicated, but there's a dusty torus that if you try to see the quasar in this plane, you would see a very different object. It would be obscured by this dust torus. And so there's continuum emission and line emission from quasars. The continuum can be both thermal emission from this disk and non-thermal emission, which has to do with this jet or with the hot corona that forms very close to the black hole. And then there's line emission, which I already said, broad and narrow lines. So one important point for our discussion is that the thermal emission in particular is stratified. So this is just a cartoon where it shows the black hole is here. This is the accretion disk. So now I'm talking about just the thermal emission from this disk. And this is stratified in a simple steady state model for this disk. You must have something like this equation where you say, well, I'm liberating some, well, in order for the gas to accrete, it has to keep releasing its binding energy. So the luminosity must be something like Gm m dot over r. So Gmm over r is the potential energy of the gas. M dot is the rate is flowing in. So this is the luminosity that corresponds to the rate of release of binding energy of the gas. And if this is converted into photons, the photons are coming out by assumption here as a optically thick disk. So the photons are just coming out as a black body emission, sigma t to the fourth times the area, pi r squared, of a particular annulus. So this equation implies that the temperature of the black body emission goes like the radius to the -3/4, which means the inner part of the disk is hotter and the outer part is cooler. So if you add a bunch of black body spectra with a range of temperatures, you get what is sometimes called the multicolor black body disk, spectral energy distribution. At very long wavelength, you see the Rayleigh-Jeans tail from the outermost part of this disk. In the Wien tail, you see the innermost part of the disk, which is the hottest. Okay, and now we're going. If you stick in a binary here, you're going to modify the emission. I just also want to show you this is an actual observation. So this is presumably this continuum over here, and these are all the various emission lines. I should say if you take so this spectrum here, yeah, I don't know why it's so slow. This spectrum is in the optical UV band, which corresponds to this thermal emission. If you take a broader view of quasar spectra, which is shown here, the thermal emission part is just from this disk, which is here in the optical UV. But quasars, this is a template from an atlas of many quasars and their average spectrum, which extends from the radio all the way to the X-rays. I should emphasize that the radio and the X-ray emission have components. The radio is entirely non-thermal emission, presumably associated with these jets. The X-ray emission also comes from the jet and from hot gas that's hovering above and below the accretion disk here, which Compton scatters the photons into higher energies and produces up to hard X-rays. Okay, so now that this is clear, let's do the simplest possible thing, which is I showed you that the accretion is periodic. So if you replace this picture by saying I have a binary black hole and it's producing some thermal emission in the inner region, that's the simplest thing and the most robust thing to think about. You would expect it to look like, roughly speaking, like a quasar, but it's going to be periodic because the emission is periodically modulated by the periodic accretion. So people have actually started doing this. There are 3 large searches for periodic quasars. Of course, if you want to look for periodic quasars, you need to have a data set which contains many, many quasars and time domain data sampled, their emission sampled over long periods. And there are some surveys where you can do this. So this is our own group at Columbia. There's 2 other groups who've looked for these in large surveys. And these I'm listing the current results from these searches. So there's something called Katarina Transient Survey, which contains 250,000 quasars. At the time of this paper, there were 10 years of coverage, and roughly speaking, regular data points every 2 weeks to this particular magnitude limit, which just means that you can only really look for quite massive 10 to the 8 or 9 solar mass black holes in such a survey. And so they identified 111 quasars whose periodograms showed periodicities between 1 and 5 years. And this covers actually most of the sky. Our own group looked at another data set, PTF, Palomar Transient Factory, which also covers more than half of the sky. Compared to this, it's deeper by a couple of magnitudes. It has a shorter baseline of 5 years, and actually this survey was not really designed for a systematic search. This was going after supernovae, and they pointed in various regions of the sky in a very non-uniform fashion. So there's a very non-uniform sampling. Some parts of the sky have only 3 data points over 5 years. Some have hundreds of data points. But you can still do the exercise of looking for periodicities. So we identified here 33 candidates whose periods are from a couple of months to a year. So they're more compact and slightly lower masses than this one. And then recently, this is a typo, there's another survey which is kind of a follow-up to this, the Zwicky Transient Factor is ZTF, this should be called ZTF. And they combine it with the Sloan Digital Sky Survey, and they found 120 candidates with periods again between 1 and 3 years. These are the total number of quasars in these data sets. So just to show you examples how crappy these look like when you actually try to find them in the data. This is an example from Maria Carisi, who's a PhD student at the time at Columbia, from her thesis. These are data points for 2 of our objects which we identified as periodic. And these are the best fit sinusoids. If I showed this, well, it's kind of hard to see by eye. You can actually still take a Fourier transform. And this is actually a very non-trivial exercise, because what you do is you take a Fourier transform with this kind of data, then you see a peak, then you have to ask yourself, well, is that just noise or is that actually a significant peak? So to assess that, you have to do many, many Monte Carlo realizations of, if you take this entire survey of 33,000 quasars in this case, and I'll show you in a second how you mimic the noise. How often do you find a peak? Yeah. Yeah. So you basically create mock observations. So you do Monte Carlo realization where you know exactly how the real quasars were sampled. And I'll show you in a second. We have a noise model for how quasars flicker. So you create a mock quasar and you sample it exactly the same way as the quasar number 1 was sampled in the actual survey. You create another random mock quasar, you sample exactly how quasar 2 was sampled in the survey. You do this 33,000 times. Now you have one mock survey. And then you can take a periodogram of each object and you'll see some peaks. Then you have to repeat this whole exercise at least hundreds or thousands of times to quantify how often you get fake peaks. That's the exercise we've done. Yeah.
You have a higher volume.
Sorry?
Do you have any causes that have produced very hard X-rays?
Yeah. So the hard X-rays are supposed to come from a corona. So over here, and actually nobody understands the reason that there is a hot corona. But beyond this model of the I don't know why it's so slow. So beyond this disk, it has been empirically established that over here, at just a few Schwarzschild radii from the black holes, there is very hot gas with a geometry that has the size of few Schwarzschild radii and is above and below the disk. And what it does, this hot gas, it Compton scatters photons that are produced near the black hole up to high photon energies. And those are the dominant contribution in hard X-rays. Okay, so the problem, so now the question is, did we really find binary black holes? Yeah, question. This one? No, maybe it will be clearer. So you take the actual data. I'll show you in a second. You take a Fourier transform, you find the peak. Sometimes you don't find, it looks a wiggly Fourier transform. Sometimes there seems to be a clear peak in the Fourier transform. And then you have to ask yourself, is this object really periodic because you see a peak, or is this simply some noise? Now I'll explain what, and it's the noise that you have to model many, many times because you have to find the probability distribution of these Fourier transforms, which is a stochastic process. So you can get a fake, and actually I'm going to explain this next because I think this is the most interesting way to look for binary black holes. And and therefore it's interesting to ask how you actually make sure that you see periodic objects and their binaries. So this is the issue that you actually asked about. So we know that all quasars flicker all the time on all time scales. And again, it's something that physically has not been explained. This could be due to local instabilities, or it could be due to how this responds to radiation. We don't really, well, it would be nice to understand the physics of what causes quasars to flicker, but we have hundreds of thousands of quasars, and we can characterize the fluctuations in their luminosities. It's a stochastic process. So the idea is that the quasar variability is well modeled by a Gaussian stochastic process. There are many ways to explain this. I am actually half cosmologist, half astrophysics. So for me, the intuitive understanding is the noise model, which fits quasar variability, is a Gaussian random noise, which means it's better to think in Fourier space. And each quasar, its light curve, as a luminosity is a function of time. If you take a Fourier transform, then you have a bunch of sine waves you add together, and at each frequency or each wavelength of sine wave in your Fourier decomposition, you just pull a random number from a Gaussian for the amplitude. That's called the Gaussian noise model. So in that case, what you can talk about is the power spectrum. This is the power as a function of frequency f, or basically the variance at each frequency. And empirically, again, no physical understanding, the power spectrum of quasar variability is modeled by this broken power law, where this is the frequency f. So at low frequency, when f is small, so sigma is an overall amplitude, tau is a characteristic time scale, or inverse of tau is a characteristic frequency, f is the frequency. So if f is very small, smaller than, so the tau f is small, then this is just a constant. So power spectrum is constant. So at low frequencies, this is white noise. At high frequencies, when this f is large, then this term dominates, and it goes like f to the minus 2. So that's red noise. So this is a broken power law power spectrum of a Gaussian field. Yeah. This is the Fourier. So I'm talking about a light curve. Luminosity is a function of time, and you can take a Fourier transform. F is the frequency, replacing time. Yeah, you take light curve of quasar, you take Fourier transform, and f is the frequency. If the quasar was a perfect sine wave, then this would be a delta function at some frequency f. Instead, it's a broken power law. Now again, because I'm a cosmologist, I have these conversations with my quasar friends. They don't think this way. But I don't know how many of you are familiar with the concept of a correlation function and the fact that the power spectrum and the correlation function are just Fourier pairs. Do you know this? So another way which is useful to think about this is in terms of a correlation function. So now you take the flux of a quasar, you evaluate it at some time t, at some other t, which is delta t offset, and you take an average of this. So that's like a variance, but offset in time. That's called a correlation function. And I'm not going to do the proof here. In a few lines, you can prove that for a Gaussian field, the correlation function and the power spectrum are inverse Fourier transforms of each other. And so this correlation function corresponds to this power spectrum. And so another way of thinking of quasar variability is the variance. So now it's in real time instead of Fourier space. The variance of the luminosity or flux of the quasar is some number sigma squared, but then it's depressed by an exponential. Tau is the time scale, and if the two times you're evaluating the fluxes, they become decorrelated when you take 2 points farther than tau. If you take 2 points closer than some tau, then it's very correlated. If the quasar was very bright on Thursday, next Tuesday it's likely to be bright still, but 6 months from now it's random again. Now you can take this model and you can make random realizations. You can create your own fake quasars, and this paper showed in 2016 some examples of these are all just random fake quasars, and you can get things that look like this. If you generate enough light curves, eventually you'll find in your mock survey things that look very periodic. And this is a big caveat, because now you have to say, if you go to an actual data, and you find something like this, and you take a Fourier transform, well, maybe it was just random noise, flickering. So that's why I said, in principle, you have to, I should just emphasize, you can still convince yourself, like we did, that we generate many examples. You know, maybe I should just say this tau is of order, let's say, months, and this sigma is of order 10%. So quasars vary by roughly 10% in their flux randomly, and this characteristic time scale is a month. Yeah. Yes. So p-value, which is listed there, there's only a 10⁻³ chance that the peak in the Fourier transform of this curve, only 10⁻³ out of random survey realizations had a peak that tall. So that basically tells you what we've been doing. But what does this mean? Well, I think there's still some issues. So first of all, when you calculate this p-value, and again, I think this is the kind of best you can do, but it still depends on your noise model, because if I change this noise model a little bit, I can still create fake periodicities if I have some noise model with some little more power at low frequencies. So you'll never 100% convince your colleagues that these are genuinely periodic sources. Problem one. Problem two, okay, it's periodic, but that doesn't mean it's a binary. Maybe something else causes the periodicity. So big question, how can you tell that you found a binary? So now I want to say, well, again, spoiler alert, there is no case, we do not have an example where everybody agrees we found a binary, but there are some compelling cases, and at least you should see how we try to convince people that they are binaries. So I show you a couple of examples and how that relates to these emission models that I discussed for binaries. So this is one example of a binary. It's called PG1302102. It's one of the quasars from the Catalina redshift survey. This here is the light curve in magnitudes. You can see 14.7, 14.9. This is kind of 10% variability. This is in days, so this extends 20 years. And you can see, well, it's kind of looking like, you see a couple of cycles of a sine wave. There's some historical data, goes back 20 years. And this was one of the objects that was pulled out of these surveys as a big peak in the parallelogram. The mass of this quasar is inferred from the broad line, the width of the broad line. I can tell you more about that if somebody asks, but it's a 10 to the 9 solar mass black hole. The orbital period is 5.1 year. This is observed, but the redshift of the quasar is 0.3. So this is intrinsically a four-year period. This was found among 250,000 quasars, one of the 111 in this survey. So how do you know this is really a binary? So the first thing you could say is, I told you that if you take a periodogram in the simulations, you find some structure that is not just a single peak. So if the mass ratio is larger than 0.3, I told you the periodogram should have a largest peak, which is not the orbital period of the binary. It's a factor of few larger. It's the orbital period of the cavity wall. So this is a simulation of a Q of 0.5 binary, and this is the periodogram. And you see actually two peaks, and then the biggest one is at several times the orbital period. If you take a more unequal mass binary, then you should just have a quite nice peak at the orbital period. So one thing you could try to do is find in the periodogram 3 lines roughly corresponding to the orbital period, roughly half the orbital period, and a factor of few higher peaks. So this is this object, and this is its Fourier transform. This is the light curve. This is how it was sampled. And this is the light curve of the quasar, and this blue is the periodogram. So we got very excited first because this blue here, periodogram shows a big peak over here, and then 2 peaks over here. This is the blue, is the data. So at least in principle, you would think that's a way to convince yourself this is not just random noise, it's a binary. So it turns out that this is a cautionary tale, because it turns out that this blue structure in the data that you see is entirely caused by aliasing. So the red over here shows a sine wave, so just a single sinusoid, and you sample it exactly the same points as the data, where the data was taken, and then you take a Fourier transform. And then that's the red periodogram here. So you see that the structure of the 3 peaks is actually not because there are 3 periodicities, it's 1 periodicity, which produced additional peaks due to the way that this was non-uniformly sampled. So unfortunately, there's no proof for this object from this, that this is a binary. But at least in principle, you could try. Nobody's done this. In principle, that's a way to go forward. Try to evaluate more complicated statistics where you look for structures containing 3 peaks, and you, in your noise model, including that's actually what you asked about, how you incorporate sampling. You have to create mock data sets with the correct sampling and ask how often you get these 3 peaks. Nobody's actually done that, but that would be a good way forward. Let me tell you something that I think does indicate that this is a genuine binary, which actually works, I think. So suppose you try to explain this and forget all our simulations, and you take only one result from the simulations, which is that the real binaries, if the mass ratio is small, below 0.05 or 0.04, then you don't have variability from hydrodynamics. It's steady accretion on the secondary black hole. If that's the case, then you can think of the secondary black hole is a light bulb. It's steady, it's moving around. It's moving around the primary. The primary is accreting very little. Now you have a moving light bulb, and the velocity, this is just the Keplerian velocity as a function of mass ratio, total mass, and period. If you plug in the numbers for this quasar, the orbital period is 4 years, the mass is 10 to the 8.5, Q we don't know, so let's leave it as Q. Then the velocity is 9,000 kilometers per second. So that's actually quite a large velocity. That's 7% of the speed of light. So now you're saying if it's a binary with some small q, it's moving around at whatever 7% of the speed of light. So there will be a line of sight component that you have to multiply by the sine of the inclination. And in this case, now you have a light bulb that's moving at high speed, so you have relativistic Doppler boosting of the emission. The Doppler boosting says that if you have an intrinsic flux at some frequency nu, then the observed flux will be this factor here, the Lorentz factor times 1 minus beta times cosine theta. Beta is V over C, and cosine theta is the orbital phase, and sine I is the inclination. And this, if the emission is a power law, so alpha here is the local slope in the spectrum at your observed frequency, then you boost the observed flux by this d to the 3 minus alpha. And if you expand for small v over c, then this change in the flux is 3 minus alpha times v over c times the line of, take into account the line of sight component only. So if you want to explain 14% variability, it could, and which actually looks quite sinusoidal. If you want to say, well, this could just come from relativistic Doppler effects, it looks quite sinusoidal. And if you want this number to be plus or minus 10%, you need 20,000 kilometers per second, which is actually possible if you take the mass to be a bit larger and Q quite small. You can explain this 22,000 kilometers per second. Maybe, well, this is just numerically converting this to constraints. So if the total mass in your model is large, 2 times 10 to the 9 solar mass, which is well within the errors, the mass ratio is low so that the secondary moves fast. And the luminosity is mostly coming from this secondary. It's not contaminated by the slowly moving primary and is not too far from edge on 30 degrees. Then this sinusoidal curve is reproduced just from Doppler beaming. So that's just a different model for the periodicity of this quasar. And now you have to say, okay, but Zoltan, how do you know that this model is correct? So the good thing about this explanation is that there is a test for it, which is, as I said, the flux variation goes like 3 minus alpha. That means if the local spectral slope at 2 different frequencies is different, then you expect, this is just kinematics, this is a light bulb moving around. But the amplitude of the variability depends on the spectral slope. So again, that's kind of intuitive. If you have a steep, if you're looking, this is a spectrum. You're looking at some particular frequency, this frequency, and now you're moving due to Doppler effect left and right. If your spectrum is steep, you have more variability in the amplitude. If you have a very flat spectrum, you move it left or right, you have lower variability. And it turns out that this object, this is the spectrum, this is the UV, this is wavelength, this is the spectrum. So as I said, this object has data going 20 years, but that's photometry, just in a couple of bands. But it does also have, it's a very bright source. It has a spectrum in the Sloan Digital Sky Survey and with GALEX in a UV telescope. And you can see the slope is actually different. In the optical V band, the slope is 1.1 over here. So you expect 3 minus alpha, this constant is 1.9. In the UV, the slope is minus 2. You expect 3 minus alpha to be 5. That means in the UV, in this cartoon model, you expect exactly the same sinusoidal variability, but it should be 2.5 times larger amplitude. So then I was very proud of myself because I went to the Space Telescope Science Institute archive and I actually found some data in the UV from Hubble and also from GALEX. And this shows the light curve in the optical, which I already showed, this one, the black. And these here are points from Swift, GALEX, and Hubble, this. And then we actually went ahead and proposed new observations in the optical and the UV and the Swift telescope. And so now you have an optical light curve for this object that looks like this. And in the UV, you have a 1 point here, and then you have a bunch of points, and then these are new points. And I'm happy to say these are miscalibrated by Swift. I should correct them. They actually lie right on this curve. So it looks quite, maybe not a smoking gun, but it does look like in the UV. Sorry, the blue is the best fit in the optical that I already said, with the 5.16 year period. This blue curve here is not a fit to the UV, it's the same curve multiplied by 2.6. And it seems to go through the UV point decently well. So I think that looks modestly compelling, that you're actually seeing a high mass, unequal mass binary modulated by Doppler effect. Certainly this is something that could be done much better in the future if you have multicolor data. In the optical, unfortunately, the slopes are not super different in just nearby optical bands. But if you had, there will be large optical and also large UV surveys in the future. And if the slopes are different, you can do this test. Okay. The boss is not here, but I think I have about 10 minutes. So let me at least say one more thing, which is very particular to binaries. And maybe I have to skip the math, but there's another thing. I think I'm going to skip this math and go to the cartoon. So the idea here is that if you have a binary, there's periodic emission, either due to hydrodynamic modulation or due to this Doppler effect. But there's something else that should happen periodically. If the binary is not completely face-on and is close to edge-on, then in principle, sometimes the one black hole goes right behind the other black hole, or maybe slightly above and below. And then you can actually gravitation lens the emission of the background black hole with the foreground black hole. Now, this lensing is, of course, very important, even just to create an image from one black hole itself. So before you talk about binaries, everybody knew from 2014, if you saw the movie Interstellar, that black holes actually look like this. This here is the picture if you had an infinitely good telescope, like they had in the Hollywood movie. And you probably also, well, you actually probably also heard that this is not a cartoon. This is an actual, they actually solved the geodesic equation for the movie with a big computer. And this here is a thin disk. So this is a multicolor disk that I just described, placed in the metric of a black hole. And you see the disk emission is coming above and below because of gravitational lensing. The path of the photons is not straight. They go around the black hole. So you see as if the disk was actually face-on, even though it's almost edge-on. In the movie, the only trick they did is they took out the Doppler shift in reality, because apparently then it doesn't look so nice in the movie, but this disk is actually moving around at high relativistic speed, so one side should be much brighter than the other due to the Doppler brightening. So that's not included in this picture. Since after that movie, we also have actual pictures of the black holes, as I described, from the Event Horizon Telescope. We have our own, I already went through this. This is our own galactic center black hole. It's a 4 million solar mass black hole. This is a billion solar mass black hole in the galaxy M87. They both have the hole in the middle. And this one, I think, is just noise. This one is an actual brightening due to the Doppler motion of the gas surrounding M87's black hole. So we know that this gravitational lensing happens and modulates how black holes look like. So we just recently, the postdoc at Columbia, we asked ourselves, well, what happens if there are two black holes, both of which were emitting in this shape, but then you look from the Earth and one is behind the other. Now you have to do this lensing again. The foreground black hole will lens the background black hole, and you can ask, how does that look like? This is the movie. Well, I should say that this is not a simulation. This we just painted the disk emission around one of the black holes, but then you already did solve the geodesic equation in an approximate binary metric. So the actual calculation here is mostly following the photons and calculating the lensing from a toy model emission. You can see that they look like the interstellar, except for the bright part, and they go around each other, and then you get these nice complicated looking images. Of course, you can't resolve, and this is something you can't resolve. But you can sum up all the emission and create a light curve. And this is an example where there are 3 snapshots shown here. This binary is nearly edge-on, 90 degrees inclination. This is normalized flux as a function of orbital phase. And you see a very peculiar feature. Every time one of the black holes goes close to behind the other, you get a flare. And then, in fact, when you try to lens the emission from the hole that's missing, you get a dip. And so that's basically an inevitable consequence of just lensing, as long as you align this system such that basically the size of the strongly lensed region, which is called the Einstein radius of the lens system, is comparable. If the Einstein angle of the lensing system is comparable to this hole, you will get these flares with dips. And even if you don't get the dips because you're not so closely aligned, you still get recurring flares. So that's interesting. You could look for these flares, and then just to our amusement, there is an example of this which we found in a unusual way. There's a quasar which we call spiky, affectionately. This one was found not in the quasar survey. It was found in the Kepler telescope survey. In case you don't know Kepler was built to find extrasolar planets, looking for transits of the planets in front of the stars. Therefore, it has very high cadence. It monitors things extremely well in photometry and very high cadence. I forget, minutes or hours. So that's completely different from a quasar catalog, but it does have a bunch of quasars in it. This is the light curve over 3 years of one of the quasars that happen to be in this field. This is the magnitude, and you see the stochastic variability, and then you see this flare. When you zoom in on the 1 month around this flare, it looks like this. This is the data, and this model is a lensing light curve. If you see that, I don't want to emphasize, but Jordi thinks there's even a dip there. So this is only 3 years, and actually happened a long time ago. But this is a model you can make predictions. So we actually have some data, and I don't have an answer at the moment. But these flares, in principle, should recur. So there should be one actually, I believe later this year. So we try to get more data. There should have been actually 4 flares that we already missed. So that's another way to confirm binarity, to look for recurring self-lensing flares. And I think I'm going to have to stop here because I've spoken for almost an hour and a half. I think what I have to do is finish a couple more, well, spend maybe half an hour more on these electromagnetic signatures next time. I think for now I want you to ask me questions, and then I'm going to ask you to vote what to talk about tomorrow. Yeah, so thanks.
Questions?
So again, this last part on the lensing simulation. So the space-time metric in that case is of a single black hole, or is this the two?
No, it's an approximate binary metric. So it's essentially two Schwarzschild metrics were concatenated into a binary metric.
Questions?
No. So I think spin actually causes additional asymmetries in the lensing. I don't have offhand the answer how big the effect that would be, but I think if you're very lucky and you have a close alignment, I think spin should definitely change the light curves. Of course, this is a toy this is theorist world. I don't know the answer whether that's extractable from data. The hope is that if you see a very compact, the hope is that if you see a compact source, this of course will be superimposed and this will be noise in the X-rays, just random fluctuations, which we also know happens in X-rays of quasars. But if you see a compact source where this orbital period is days, and you have tens or many dozens of flares, you can potentially average out the noise and these features will emerge, and yet to be quantified.
Questions?
Sorry? So I think the best, so there's two ways to do this again. One is just to look for surveys of quasars and look for these flares. I do have plans to do that. We haven't done it. It's a little harder than just to look for periodograms because you have to define what exactly you mean by flares.
No, but you have apparently a good candidate for
Oh, for that particular. Yeah, so yes, we actually have already collected data, which we're analyzing. So we have actual data. So I think we'll have some, and yeah, ask me in 2 months. But I should say the best way to do this would be, in principle, what I wrote there for LISA binaries. If you identify a gravitational wave source with LISA, and I will talk about this tomorrow. But if you find a source with LISA that's not yet merged, and you roughly know where it is on the sky, then you can target observations and look for these flares in LISA error box, and that would be quite convincing if you find these flares.
So thank you for the lecture. These flux is actually for two black holes of more or less the same size.
Yeah.
If they're, for instance, much smaller than the other, what would change on the dip, maybe?
Yeah. So the biggest feature would be that in that case, they will be very asymmetric. Whenever the big black hole is in the front, the lensing effect is much stronger.
Mm-hmm.
And in fact, we think the secondary is brighter anyway. So you have a much bigger flare when the primary goes in front.
Mm-hmm.
And you have a much smaller flare when the secondary goes in front. So you see a pair of flares, big, small, big, small, big, small.
Okay.
Same with the dip. The dip will be a much larger feature.
Okay. Thank you.
So, I mean, if you want to be optimistic, you could say the ratio of these pairs actually tells you the mass ratio of the binary modulo, or something about their mass ratio or the luminosity ratio combination.
Hi, thanks for the lecture. So, in your opinion, which is the strongest candidate for to confirm a binary system in a particular source?
Yeah. So I actually don't have a. So I think, well, I already told you about two, and I think these two are. That's because I think these two are probably the most compelling. There's a third object, which I don't have a slide at the moment. Have you heard of, there's a blazar called OJ287. Raise your hand if you heard of OJ287. Wow, nobody. So there's one more periodic object, which was not found in these surveys. Is, let's say, famous because it has data going back 100 years, as opposed to 10 or 20 years. Because it's so bright that it was already seen in photographic plates in the early 1900s. And that object has a 12-year period and has a pair of outbursts every 12 years. And it's not sinusoidal, it's like a pair of bursts. And the model for that is, actually the story is a bit long here, but I mean the rough model for this is that it's a primary black hole that's very massive, and the secondary that's not coplanar with the disk of the primary, but tilted on an eccentric orbit and crashes through the disk twice per orbit. And because it's eccentric, whenever it goes to near pericenter, it crashes through the disk, goes around quickly and comes back. So they're a pair of flares. They come in pairs. And that looks to me quite compelling, that it's a binary, that model. There are some details I can tell you.
So in your opinion, this is the strongest candidate, the OJ37?
Yeah.
And sorry, I did not pay attention, but what about millisecond pulsars? Is this source or some other sources already been detected by this method?
Millisecond pulsars. So far all my talk was about massive black hole binaries, not pulsars. I will talk potentially tomorrow about stellar mass binaries.
No. I was talking about this indirect method for detecting gravitational waves from supermassive black holes, an array of pulsars, millisecond pulsars.
Oh. Okay. The pulsar timing arrays are monitoring a bunch of pulsars of order dozens to look for gravitation waves. The situation there is that there's no detection of a black hole binary. In fact, there's no detection of gravitation waves yet. There's, again, sorry, this is a long answer, but if you follow, I don't know if this came up. There's currently okay, how do I say this? There is currently an intriguing claim that there's correlated variability in all the pulsars. They go up and down. You know, the timing modulations are correlated in all the pulsars. So that's consistent in principle with gravitation wave passing through the Earth. If this came up earlier in the week, this makes sense, right? So when the gravitation wave passes the Earth, and we are at the minimum, all the quasars in principle should shake together. All the pulses should be delayed from all the pulsars, and then half a cycle later, all the pulses should arrive early. They should be correlated. But if it's really due to gravitation waves, there should be also a modulation on the sky, an angular pattern of this modulation, not just this monopole. And they have not yet announced that they've discovered that they have evidence for this modulation on the sky. But in principle, they could very soon be announcing that. And then we'll have a detection, which will be very exciting, of the stochastic background of gravitation waves, not a single black hole. Okay. Now, they in principle could detect also a single black hole binary's gravitation waves. That requires probably another decade or so of monitoring these pulsars.
Okay, let's turn to the speaker again.
Well, wait.
Yeah.
So I have to ask you quickly a question.
Yeah, for tomorrow.
Tomorrow I'm supposed to give my last lecture. If you can raise hands quickly, then I can take you. If there's some overwhelming preference. I have two topics I could be discussing. One, well, first of all, I need another half an hour to finish discussing electromagnetic signatures, and then we'll have an hour left or so. Topic one, keep discussing massive black holes and where they come from. We think they formed in the early universe. Topic two, after LIGO, everything I said can be extended and discussed for stellar mass black holes. And so we could discuss where do the LIGO binaries come from? Do they produce electromagnetic emission? These are the two options. So I just want, no obligations, just genuine interest. If you prefer topic one, go like this. If you prefer topic two, go like that. Okay, I detect strong preference for topic one. So So apologies for people who want me to chat privately about stellar mass black holes. It's very exciting. I'm happy to chat, I don't know, lunch or dinner or coffee.